start recording. Well, I've seen that you have seen that there was, let me change the gallery view. Okay. A problem with the recording of two classes back, and I couldn't recover the corrupted file. It was a problem regarding Zoom that crashed during the meeting. And so I have the recording file, but the recording must be converted by Zoom, and conversion doesn't start. I've opened a ticket for the Zoom service for recovering or something like that, but they didn't succeed. So the first part of the class is on the web, but doesn't matter because it was just a short summary in the class after. So I think that nobody has the problem of something missing in any case. Well, what we have to do today, first, just look on our web. Where is our web? Yeah, this. Okay. This is this week, our web. Just a comment on the contents. Can you see the screen?
Yes, we can see the screen.
Okay. So because sometimes I have problem in sharing the screen, I share the incorrect window. So you see here, it is my view. There is the well. First, let me notice you the short document that is not a new topic, but just to clarify something that was in the slides, in the previous slides. Let me open now. So very short, just a few comments on this. It was an addendum to the POSIX Essential regarding creating files, and we need that also because in the next step we will see that we will create a file for the exchanging data, that is the make FIFO, and we will see it's the pipe method using a named pipe. In any case, when you have a create or a create a directory, a change mod or something like that, you must specify file permissions. It is written, but it's not clarified which are the parameters, which is exactly the syntax of that. In the system call, when, for example, creating a file, we must specify the permissions. It's a variable of a standard, of a predefined type that is called mode T. Mode T is something that is specified on a header file, that stat.h, that you include. And if you want to exactly know which are the symbolic specification of that mode, you remember that we saw that in working with the shell. Modes are read, write, execute for the owner, for the group, and for all other users. And you must specify when you create a file, which are the permissions to the owner, to the participants of the group, and for the other users. All modes can be found in a man page. Everything is a manual page, but sometimes it's difficult to find out. In the command change mode, CH mode, that is in the section 2 of the manual. You can find all modes. And here is the synthesis of relevant modes, the one that we use in exercise, for example. So you see that they are called masks. The symbolic name is this one, for example, IRWXU, and so on and so forth. So it's difficult to have in mind, and it doesn't matter. Usually you put a mask, for example, that read, write, and execute. If you don't execute, if it is not an executable file, you don't need to put the X permission, so you can separately specify read or write, and so on. These are for owner, for group, and so on. These masks, this is the symbolic name, and this the corresponding bitwise value. The bitwise value is, so you can specify in numerical form, or better in symbolical form, with the S as a prefix. This is an example. For example, create a file whose name is pick in the current or working directory, and these are the permissions. Why 3 permissions? Because since they are bitwise names, you can compute the OR, the bitwise OR operation. So it's a superimposition of the 3 masks, whereas in every one there is a one digit. It becomes the 1 digit for the all masks. It's OR operator, and it's usual to do that. So in this case, for example, you specify, we will see in this class what is the make FIFO. That is a sort of creation of a virtual file for making 2 processes to communicate each other. And you open as a file, and you specify that the file has the capability, in that case, of being read by the user. So it's very simple. So this content was already in the first pack of slides, but it was simply said that there was the mask of the capabilities for the file. So you know what to write exactly, and where to find all possible values when you create a file, hard file, the file on the hard disk, so regular file, or a memory file like the FIFO we have seen. Okay, this was one of the first. Okay, you can find this just to avoid to go inside the man pages to use the correct symbols. Here we are an exercise that we will open next hour, and I will propose you to work on it in the same way you do usually, as to say, in groups, and carry home partially the solution. The first file is a sort of story. You can read if you want. Not necessary, but it's just a comment on the shell scripts used to make the lottery we will do next, as to say in scientific terms, how to generate or how to ask Linux a random number, just to select one of you to present his or her solution to the exercise of last week. Stop share, we go back. So the recording is on, and now some of you, as I've met some of you in the Saturday meeting or using the Skype directly for, so I will, I'm saying, remember you that if you need some help or to ask some question, so Skype me a message, and usually I have time, so we will decide to have a short meeting directly one-to-one using Skype for questions anytime, potentially anytime. So I'm not available anytime, but usually it is possible. So last week you have discussed it together in groups a problem that was the problem of having a master process which had to fork twice, generating two sons, and making the two sons to carry out some very simple numerical problem, as to say, to sort an array. So the numerical algorithm is absolutely not important. The idea is to learn how to organize that concurrent program. In the video clip, for the Saturday video clip, I also talked about the fact that usually this kind of problems are purposefully solved using a master process, the one that you run at first, who forks as many times as needed to generate all sons, and so that all sons carry out the job. And the master, the original process, stays alive and controls the sons and waits for the sons to exit at the end, and so it is able to exit itself. And in some cases, the master can also have the interaction with the user, for example, in this case, for example, but not necessarily to input data, send data to be computed and by to the son, and receiving back the results, and so having the complete dialogue with the user. But it's not necessary. Also, the sons could input and output and interact with the user. But the idea is that in general, even if it's not mandatory, to keep one process as the master of all processes, like we do in thread programming. So these were general suggestions. I have addressed this also in the video. Now I'm asking, well, we can, of course, we can draw a number, a random number, and choose the person. But first, it's an amusing joke. Maybe if some of you has solved and spontaneously wants to explain and to present the solution and show that it works and comment the code, please, one of you, who is the one man or woman who wants to present. Otherwise, I will choose randomly one and ask, did you solve that?
Hi, Professor. Marco Fedozzi here. If you...
Who are you?
I solved the code. It's not the most elegant one.
I can't see you. Who are you? Please open.
Marco Fedozzi.
Ah, Marco Fedozzi.
The one with the camera.
Okay, with the open camera. Marco Fedozzi, the lottery had chosen Marco Fedozzi. So please I think that you can.
For the moment, I cannot share the screen.
You cannot
share the screen.
Share?
No, it says that the sharing of the screen has been disabled.
Now I think it's advanced.
Let me check how it works.
All participants. So, okay. Now I think you can.
Yes, I can. I think there's a lot of delay in the audio, but yeah.
Good.
Can you see the screen?
I see. I asked all students if they can see the screen.
Yes, I can see the screen.
You can. Well, it's a. Can you enlarge the screen or?
Let me check. I mean, I cannot enlarge the screen. I can probably work from the configuration. I don't know. I don't know if it's here. I never tried this actually.
Okay.
So if you have any suggestion, let's see.
No. Well, it's in the. Okay. One possibility is just to open as a file, as a text file. You're opening what? I can't.
It's with Notepad++. It's a simple editor.
That should be.
Let me see. Yeah. Oh,
zoom,
wait.
Zooming.
I don't know. I
don't
think I solved anything.
In the visualizer,
yes.
Maybe there is some like zoom.
Yeah, it is. Okay. It was easier.
Control what? Control no. Oh.
Yeah.
Bigger.
Easier than expected. Okay. Is it?
Fine. Beautiful.
Stop. Yeah. Okay.
So explain the
I probably
structure
have to scroll
of your code.
Okay, it's probably not the most elegant, but it works. At least for what I tried. So we have the main process, the father.
Yeah.
That has some variable here. Those are the two pipes, the two.
There will be pipes.
Array of file descriptors. Yes.
Yeah.
This is the simple array where I'll put the data. And those are strings that I will use to call the two childs. We'll see later. So I have the ID for the two childs here and the boolean flag. First of all, opening up.
Well, do not jump too much from one line to another line. So
okay, sorry.
It's difficult to. Okay, so we see if pipe. So the first pipe is
the opening of the two pipes.
Two pipes.
Error checking.
Two pipes and error checking.
Yes.
The message. Okay. Yes. Good.
One pipe is for father to first child communication, and the other for first child to second child communication. Then we have the first fork here, again, checking for possible errors. And here, if I'm looking at this inside the first child, I will first of all close unnecessary pipes.
Good. So you have followed the idea of having the father separate from the two children, okay? So the father keeps in computation, and the two children separately carry out the job. Okay. Are you connected? I think that you are frozen. No, I think that okay. Fedotzi went out and probably is trying to reconnect. Well, maybe, well, we wait a bit and I think that we have lost Fedotzi. Okay, let's go without Fedotzi. Is someone else who solved it and wants to... Oh, Fedotzi is back. Fedotzi, can you hear us?
Okay, I'm here. Can you hear me and see me?
Yeah.
Okay, sorry, network problems.
Try again.
Okay, so let me share again the screen. Okay, can you see it?
Yeah.
Okay, so where was I? I think it was here inside the call to the first child process. So, as I was saying, the first child closes unnecessary pipes.
Mm-hmm.
So the one that would be the input from first child to second, and then the output between father and first child. Then I decided to pass the parameters, the file descriptor, inside the arguments of the call to the new program that will be launched. So I first of all convert to string the file descriptor for the input.
Because this is the first child and executes directly another process. Is correct?
Yes, exactly.
It's called exec to.
Exactly.
Okay.
I call the exec VP here.
Okay, and you're passing to the executed to this process. You're passing using the interface, the standard interface. Which parameter are you passing to it?
First, the size of the array to
be
ready. Then the file descriptors.
Okay.
Where the process will read and where it will print.
Correct, because the program that is in execution doesn't know which are the
exactly.
file descriptors that you have.
I mean, probably I could have just closed here standard in and standard out for the child, and then with Zoop, I'd probably make it work. But
okay,
this is feasible again. And then with the exec, I call the first child.
Exec, okay.
Yes. Here I close for the father the unnecessary pipe, unnecessary file descriptor. Mm-hmm. Again, another fork for the second child. All things similar, just
similar to the previous one. Okay.
The previous one, exactly. Just that I have just one. This is complicated. Sorry. I have just one parameter, one file descriptor, since it doesn't have to print into another pipe, but just on the standard output. And again, I pass the array size here, and I call with the executive. Then here I am back into the father.
Okay.
I close the pipes which I don't need, and I do this.
So this is the body of the father, the true body of the father.
Exactly. I have a cycle here that's controlled by a flag. The flag comes from the read array function. This, which is down here, simply reads the parameter passed by the user into the standard in one at a time.
So the father process has a communication with the user. So inputs data from the user using this function.
Exactly.
Okay.
Then this is just input inside.
Okay. So it's just reading the values of the.
Exactly. The thing I just do to stop the entire process is if the user inputs are
good. So
and I check it here with the
is able to control all the fantastic
with a double Z, and it returns the value. And in fact, if you look back into the main code, the flag here will contain true only in the case.
So a special input to stop all the process.
Exactly.
Okay, good, fine. And so
array put simply puts this array into the first pipe, the one that communicates to the first children, and is down here.
So it sends the values to what? To whom? To
the file descriptor that's the pipe that the first child will see.
Okay.
I use the write, so it will write just row bytes. So that's why I have this multiplication, size of the array times the size of an integer.
Okay, so it sends data, the input data, to the one of the process is executed by the sons.
Exactly.
Okay.
And this is all from the father. When the flag is true, so where when the flag is false, so when the user inputted just a 0 string, we exit from the loop, we close the last file descriptor, and we wait for both children to
exit and returns 0.
Exactly.
Good.
And this is the father. Then looking at the children, we have first we check if they're called correctly.
Okay. Oh yes, if the interface is correct. Okay.
Which shouldn't be a problem if they're called by the father process, but
these are data taken by the interface, the standard interface ARC.
Exactly. Okay. So dimension, the file descriptor with the father, the file descriptor with the other child.
I stress the fact that you use the A to I, the to ASCII to integer conversion, because the argument passed through ARC-C, ARC-V are strings. So the file descriptor is a number, an integer number, but expressed as a string. So you have to convert into an integer number. I say so because this is a common question by some students. Because the interface ARC-C, ARC-V is based on strings, not on integers or any other types. Okay. So we have converted.
Yes, and we have a cycle that's very similar to the one inside the father. We have again the same array read function.
Okay, you
delta
read the
array from the pipe.
Sent you. Okay.
And then the array put, which just puts those data into the other pipe.
Your input, what is it for?
This puts the array received from the father into the pipe that will be read by the second child.
Into the other. Okay, because this son sends values to what?
The second son.
To the second process, to the second son.
Yes.
That executed the second process. Okay.
Exactly. Again, flag is used in the same way as before. And if we go looking at the single functions, array read and array put, they are very, very similar, identical to the one that were present in the father.
Yeah.
It's just a matter of the file itself. Things are a little different in, again, here when it exits from the loop, it will just print close files and return. If we look at the second son.
I missed something.
Yes.
The information about exiting the end of the process was where is?
Here, I have just a return.
The flag. It depends on the flag.
Yes, we exit from the loop.
Yeah. Okay.
When the flag, it's identical to what we did with the father.
Okay. Okay.
Since it's just different in the file that we read from and write to. So this is the second son, the one that actually computes something. But again, things are not so different. We check first for parameters, since again here array size and file descriptor of the end of the pipe were passed as arguments. And here with a to I, we pass them back into integer values. I decided to maintain both the original array and the sorted version.
So the same, okay, I see.
That's not necessary, but in case we need it again. Again, we have another loop controlled by the flag, which is, again, takes its value by the array read function that is identical to what we saw. It's just this time reads from the other pipe, and we call the bubble sorting function. It's not the quickest one,
okay.
but for the purpose of this, it was easy to implement. So calling this bubble sort, we put the sorted array into the sort R vector, and we just print it. Again, when flag would be false, so when the received array would be just all 0, we would exit from the loop and then terminate. And the bubble sort is here.
Oh, fantastic.
Nothing weird about it, just a simple bubble sort.
Good. Also, good. Very, very, very good. So,
thanks.
No comments in particular, since you have just implemented exactly the idea of the master program that keeps the control of all children, of the execution of the whole concurrent program. You're correctly, it's a very good solution because you have put all the error management, almost, I don't know, not check it if it's there completely, but most part and the relevant part. So it's a very good solution. Thank you very much, because thank you.
Thanks.
Also on behalf of the other students, because I think it's something that can be really used. So
thanks. And as I said, probably could be better implemented, as you said in the last session, similar to what shell does with the pipe function, just by instead of using two files.
We will address this problem in a few moments. And well, from a practical point of view, I suggest that you send me all your files the one they have seen, if you agree with that, and I will publish on our web. So in an easier way with respect to reading from the screen, from the recorded screen, everybody can see and discuss and copy and paste your code and so on, because I think it's a really good solution and is very good from the point of view of having a working example developed in the proper way. So
Yeah, no problem. I'll
as soon as
send you to
just
email.
after at the end of the
Yes.
class, send me and I will publish it. Probably some other students, I'm sure of that because I've talked with other students. So I think that there are other solutions, maybe different from this. It doesn't matter. It's not evaluated from this point of view, but it's the first good step in developing good programs. So
Thanks. With pleasure.
questions about, oh, thank you very much. And well, appreciate that. And but next time someone else will do. So your Fedozzi was being drawn from the lottery, the first one, but next one will be another. So questions from someone of the many students we have in the class? No questions? Good. So so we can go on, and the idea is that so you will see the published files of by Marco Fedozzi in after the end of the class. So a couple of minutes break, and we will start with another exercise that I will propose, and I will break you in small groups and start a new exercise. Okay? Few minutes, just maximum 5 minutes break. recording.
Excuse me, Professor.
Yeah.
If I read a different array, any loop, I have to declare a pipe for any loop, or I can declare a pipe outside the loop and use it every loop cycle?
Well, you can use a pipe as a FIFO for a communication, so you don't need a new pipe for any. Otherwise, you had to create a pipe, use the pipe, close, ask for another pipe. No, a pipe is forever.
Okay,
You can
because
use
I've tried it, but putting it outside the loop, it doesn't work. So maybe I've done some error in the code, and I know.
Well, a pipe is once you have a pipe, you have a file descriptor, so you can use the file descriptor for reading and writing as many times you want.
Okay.
So you must take out of a loop for communicating and computing and so on.
Okay. Thank you.
Okay. So we can start with another exercise. Is okay, everybody? I think you can hear me. Yes, I think so. Well, the exercise is very simple, but just you must put a sort of thinking of abstraction. So you have to abstract what you see in this exercise. The exercise is published on the Aula web, so please open it. It's a zip file, and inside the zip file there are three files, the three text files. One is the general description of the exercise, and two files are C codes. Let me share the screen. I think I have. Let me see where is my. Okay, questions is here. Well, pass one, read the two files and follow instruction in the headers of the two files. They are C codes. One of the C codes, or I don't remember if both, have also some errors inside, some errors to be corrected. It's just to exercise your ability in as a C language coders. You can directly compile them, and the compiler will complain and say that there are errors. Well, one of them has also a subtle error that the compiler does not detect. I think that it works in any case, but it's a good idea to try to find the error in any case. And so you must read the two files and understand what they do. As ever, you should do that before you compile and run, because you have to understand what they do and how to run them. Then steps 2 and 3 we'll discuss later, but the idea is that to learn something from this exercise, this example, and then to apply the method in this example, the method suggested by this example, in modifying the solution of the exercise of last week. Let's go to the codes, and okay. For example, I will share the second one. okay, for example, also the first one that is called P1, this is P2, is P2.c. The code contains 2 errors. The compiler discovers them, but just to exercise your knowledge about C language and POSIX conventions, please try to understand. The color of for and do are automatic colors because they are recognized as the keywords in the language, so no, doesn't matter. The code should include controls for increasing robustness. What? For example, no error checking and so on. So please find also this. This is also an example of possible exams, possible questions and during the exam. The exam may contain a code asking to answer to some questions about the code. For example, which are the errors or how to improve and so on. And after you have corrected the errors that are inside this code, you can compile and execute and to understand how it works and which are the ways. There are at least 2 ways of running this program alone, and you have to discover the 2 ways of running this program. I can try to, if I open this one, this is the other. Also, this code has 1 error. And clearly, he executes the second, the P2. This is P1. And once it's compiled, we see immediately that it executes P2, which is the connection between the 2 programs, which is why we have P2 that can be run alone, and how it is you can use alone, and how you use it executed by P1. So these are the questions no, I don't want to share, stop share. These are the questions. So please read codes, and in the file questions, there is written that you can use the method that you see from here. How you can use in your previous solution with the idea of testing separately the executed processes, not all together in one only in one concurrent program altogether. In the previous case, we have seen that we had to run the father forked and executed the 2 sons, and so altogether they could input data, pass to the first son passed the data to the second, and that was the solution, the final solution. The question is how to debug separate. Debugging means running separately the processes. In the previous case, the process 1 and 2, the 2 sons. And after you are sure that they work correctly, you put together and run the whole concurrent program. So please do what is written on this exercise, and it is also requested that you write your rule for developing a concurrent program. I think that you can understand directly from the text. So I will separate you in rooms, in group. As ever. and I'll give you 20 minutes, and then you will have some personal solutions to carry home to finally, for the next week, to change what you have, change the program that you have prepared for this week using what is suggested here. I start recording again. So next time you're in a breaking room and there is something that doesn't work, please send me a message. And I'm always here. I receive and try to understand if there's something I can adjust. Well, that you have understood, which was the aim of that exercise. Close the room, the breakout rooms. If I share my screen now with the shell, maybe you have discovered that here are the P2 and P1. P2 can be run alone. For example, P2, P2, and in this case, P2 waits for standard input because by default waits for standard input. So I write 33 and answers 33. The idea is just to put outside the same with no elaboration. But note that I can do something like this. The file, the name file is this, and the content of the file stud number is 42. And so P2 manages a parameter using the interface argv. But running P1, it executes P2 by making it read from the file, which is the meaning of that is that P2 is executed by P1, and P2 alone can run using standard input. And in case I wrote also the parameter, the file name, it also reads from another file. But it can be debugged alone. And when executed, you have seen that the executor, so P1, has redirected the standard input of P2 to the desired standard the desired input imposed chosen by P1, that was the file. So you have seen that this is made using the dup system call. That's the meaning and the purpose of the dup system call. So in this case, we have a simple concurrent program. P1 just runs the P2, but telling P2 which is the file to output, to read and output. But P2 can be debugged by alone, because in any case it has its own input, that is standard input. So we can learn from this that, thinking of the previous exercise, the last week exercise, the two children of the master process that had to receive an array, ask the other process to sort the array and output, could be programs able to run by themselves without being executed by a master process. And which is the rule that I'm asking you to write in a sentence to take into account for the future? To write codes for children, for process to be executed, so that each one receives in standard input data and maybe outputs in standard output. So you can debug the process by itself using directly the shell. And when executed by a master process, the master process, prior to executing them, redefines their standard input and possibly their standard output, so that it connects through pipes. That's the rule. That's the only rule, the only possibility we have, but it's a very powerful possibility to develop a complex concurrent process, concurrent program built on many executed processes, by executing and debugging one by one all processes, keeping them as much as possible self-consistent. So talking using standard input and standard output, so that the master process, and this is one of the main reasons why having a master process that executes all children. The master process not only establishes all pipes necessary to the communication, but also redefines one by one the standard input and standard output of each son, so that they are glued together and then they communicate. That's the idea. And the assignment for next week, the first assignment for next week, is to modify your previous solution to the problem of last week, of the sorted arrays, so that the two codes for the two children can be run alone using standard input and standard output, and when executed by the master process redefines the pipes so that they're working together. Is it clear to everybody? This is the really powerful way of debugging a concurrent program in POSIX. So strong that the shell gives you this possibility, because this is the reason why the shell gives you the possibility of redirecting directly standard input standard. For example, if your son process reads data from standard input, because when executed by the master program, by the master process, this will be a pipe, but not necessarily the standard input should carry only ASCII data, which is the one that you can type on the keyboard, of course. If you have numerical data, so integer number, numerical data of any kind, you can put numeric data on a file, and when you run your process that you want to debug, the shell redirects its standard input from the file. So data that you cannot give to the process using the keys of the keyboard can be read from a data file, for example. But so far we can limit ourselves to ASCII data. So all processes we will develop can be debugged directly using data from the keyboard. Is it clear that the principle is really important, because nobody writes a huge concurrent program by writing all the executed program, gluing all together and seeing what happens. The hope of debugging it is more or less zero. You must debug separately each process. So first assignment for the next week is redefine your master process for the array sorting and the children processes, so that the children use standard input and standard output as pipes, can be debugged separately. Then the master executes them after having opened the pipes and redefined the standard input, standard output for the children. Okay, that's all for now. Now, a new topic for next week, and we will discuss it also tomorrow. The new topic is pipes. No, not this one. Sorry. Okay. We are here, we're talking about pipe. Pipes, you know how they work, because you have already used in your exercises. Pipe is a FIFO, very simple. We will stress the concept of blocking pipe, blocking read and blocking write. So it's partially synchronous execution of the producer and consumer, since they can run different speed. So producer can produce data at a speed higher than the consumer has like reading, or vice versa. But the limitation is the length of pipe. When the pipe is empty, the consumer cannot run anymore, but it must wait for data. And at the same time, when the pipe is full, the producer stops and waits. This is the unnamed, called unnamed pipe. Unnamed because it's a file. It has 2 file descriptors. So it's a file like any other abstract file in POSIX, but it is unnamed since it has no name. That's only file descriptor. The difference is the named pipe. You see this scheme in the slide resumes exactly the idea of redirecting standard input to standard output. The work that carried out by the shell when you run processes directly, but it's exactly the thing that you want to your master process do. Because everything is a shell, everything runs new processes, it is a shell, so at the same logical structure. Named pipes. Named pipes are FIFOs, so the concept of first in, first out, so serial channel, so that the order of production, of data production, is preserved when you read. But in that case, instead of having a FIFO that known only as a file descriptor, you have a regular file it seems a regular file. A regular file is a file on disk, so is a permanent structure on some hardware. But it seems a regular file, but is, as in any case, a first in, first out policy in reading and writing. The pipe must be open, but on both ends, so it's a file. We have okay, this is an image that shows this is the file. This file for named pipe has a name. That's the difference between named pipes and unnamed pipes. So as a name, and appears to be a regular file, but it is not created with the create. Is created using a special call similar to create that is called make FIFO with the file name and the capability, so the classical capability in access that I've presented in the first part of the class. Just like create. So they are similar, that different system calls because it's a special file, it's a special characteristic. The most important characteristic is that it is not written on disk in any case. It's guaranteed to stay in memory. So it's a virtual file memory. Virtual file memory means that it is very fast, so at the same efficiency, just like pipe, that's an unnamed pipe. It's a memory first in, first out. But since it has a name, the difference is that many processes can access this. So it is possible the typical structure is that one producer, the named pipe, and multiple readers, for example. Because every process that knows the name can open, just like any process can open the same file, and one process can write, and many processes can read data from that file. So it's partially a communication system, one-to-many. In principle, there could be also more than one writer. It's not so common because just to avoid the inconsistency in data. But in principle is many to many, considering the fact that once you read, the data is consumed. So you take out from the pipe. So it's not a publish subscribe in which one datum stays until all subscribers has consumed this data. The first one reads, takes out the datum from the pipe. But it's very important, not much from the point of view of many to many, but from the point of view that is dynamic, so that it's not necessary to connect P and R with a pipe. You have seen in your exercise that the master must create the pipe. The pipe is inherited by the children, and so the sub-process, the children, are connected through the pipe. In this case, two processes, two children, or in general, two processes can decide to connect sometimes by simply open that file that is known by all processes in the system. So it is possible to connect, unconnect, to plug, unplug processes in a communication of this kind, which is efficient as much as the pipe, since there's no real file involved. And this is an example, just an example of a producer and reader. So you have main. This is the make FIFO. So someone should create the file, otherwise nobody can use the named pipe. This it must create it before all other processes connect to the named pipe. You see here that the capabilities are of reading and writing for the user. So this is a pipe, the unnamed pipe that can be used by process of the same user. The same other users, even of the same group, cannot access because they have not access to reading. So this is a file, make FIFO and so on. Is created, just creating a file, is opened. The open is absolutely the same as any other open file. And unlink means erase the FIFO in case you cannot open and so on. And write is absolutely the same, like any other write operation on file. Note the size of data types. It's data type in this case is a struct of some kind, struct data type data. So just to put on bytes, you must specify the number of bytes and so on. After you have written, unlink, make my FIFO, and so you close the file. Another process, in that case of the same user, otherwise the FIFO, the pseudo file, my FIFO cannot be accessed, opens the same and read data, simply. So it's very simple. If we think our example in which we have a master that declared the pipes for the children, and the pipes were inherited after fork and exec, in that case, the children can directly establish the connection using this kind of data. There's no difference in efficiency, because the mechanism, the kernel mechanism for maintaining the FIFO and giving access to the FIFO is similar to the pipe FIFO. The only difference is they are dynamic. So any process must know the name of the pipe in this case and use with the same policy as a pipe. This is all information that I've addressed. So multiple reads and writes are possible. And I want to point out that mutual exclusion, this is very important, is carried out by the kernel itself. So you're guaranteed, very important, differently from file IO, you could use a file exactly in the same way, I mean a regular file. Apart efficiency problem, the most important difference is the kernel assures mutual exclusion. So it's not possible that two processes write simultaneously, or writing is carried out simultaneously with reading. So no data jamming. If you remember, in file IO, there were primitives to lock, unlock the file or some part of the files just to prevent data jamming. So concurrent access by different processes in reading and writing. Here, there's no locking, unlocking, because there is mutual exclusion. If one process writes on the FIFO, it blocks other process to write simultaneously. And there is a FIFO, so you're sure that you cannot read and write simultaneously. So this is a very critical mechanism. So pros and cons, efficient and everything. This means it is not a publish subscribe system. You must know what it happens. You must know that you're reading FIFO, so the data is consumed if you read, for example. Is unidirectional. Well, it is drawback, but not too bad. The other concepts are not so important. Blocking is not a drawback by itself, because blocking, we will discuss blocking tomorrow, because it is another key point. The blocking principle is that we must prevent blocking any time we read, in particular, not when we write, but reading is something that must be assured to avoid blocking. We will see. This is blocking is the same for all reads. Any communication supported by the read system call is by itself blocking. As to say, if there's nothing to read, the process that issuing the read call blocks itself, waiting for some data. We will see that why this is a problem and which is the answer to this. Okay, this is what the last topic, and this also the stop share, and is also the second assignment for the last week, for the next week. The first assignment was to rewrite your exercise, making the two executed children able to be run by themselves by redirecting input and output. And the second is to write again this exercise using named pipes instead of pipes, of unnamed pipes, just to exercise your abilities in managing all communication primitives. After that, the part of data communication between processes is over. Tomorrow we will talk about overcoming the blocking problem, and we will start the event communication. Good. I hope that everything was clear. I asked Marco Fedozzi to send me by mail the files, that so I can publish them. And tomorrow I will send, I will write in our web, I will post that we have 1 hour class because I have some medical problems before. So we will start at 9. I tell you in voice. I will send you also a message. Okay? Thank you very much.
Thank you, Professor. Have a nice evening.
Thank you.
Bye-bye.
Professor.
Thank you.
Thank you. Bye.